Well, let's talk about weight, actually. We need weight because one of our forces is gravitational force. Weight is the gravitational force of attraction between two objects. So I've already thrown out a term, mass, right here. When we talked about inertia, we said, how do we measure inertia? Mass. Then right here, F equals ma. We have a mass in that equation, right? So what is mass? Mass is how much stuff something is made of. That never changes. The mass of an object on the Earth is the same as the mass of the object if it's sitting on the moon, is the same as the mass of the object if it's out in space somewhere. It never changes. How much stuff something is made of never changes. But weight changes. If you're standing on the surface of the Earth, you have a gravitational attraction to the Earth. You have a certain weight. If you're standing on the surface of the moon, you have a gravitational attraction to the moon. Your weight is very different there. If you're out in a space station somewhere, you're not standing on anything, you don't have any apparent weight, right? So we look at these two things. They're very different, but we interchange them a lot. And one of the problems we have is the units we use for weight. Weight is a force. And so the units we use would be newtons. Use a capital N for newtons. That's our SI unit. That's the one we'll be using most of the time. But another unit you might be familiar with are pounds. Right, that's a unit of force. Maybe your bathroom scale is labeled in pounds. And mass, mass is not a force, right? It's mass, it's inertia. And the units that we use all the time are kilograms. And in non-SI units, it's the slug. So the kilogram is a unit of mass, right? And the pound is a unit of force, but you stand on your bathroom scale and you've got two numbers there. One is in pounds and one is in kilograms, which just confuses things even more. It should be newtons and pounds, right? But they assume that you're using that scale on the surface of the Earth. And so they've done the conversion factor and listed it in kilograms. If you take that scale to the surface of the moon, the pounds will still be reading correctly because that's what it's measuring. It's measuring the force. But the kilograms will be way off, right? Because they're assuming that you're using that on the surface of the Earth. All right, so weight is this gravitational force of attraction between two objects. And on the surface of the Earth, how do we calculate it? We say the weight is equal to mg. The mass times the gravitational acceleration, the acceleration of gravity. And another way to think of where does this come from, it comes from F equals ma, right? What is F? The net force equals mass times acceleration. If you just have an object hanging in space here, and I let go of it, right, I've got a pen here, and as soon as I let go of it, there's only one force acting on it, right? As soon as I let go of it, the force of gravity is the only force acting on it. And so I can call that the weight. And mass is mass, whatever the mass of the pen is. And the acceleration is just that due to gravity. So we have a special symbol we use, lowercase g, that's the acceleration of gravity. And g is equal to 9.8 meters per second squared. And we've already used that because of kinematics, right? We've used that in our kinematics equations. Question?
Why do all objects fall at the same rate?
Well, it has to do with the fact that, and now that we're getting into forces, we can talk about that. So the question is, why do things fall at the same rate? So let's look at this one. Let's look at object A from above, right? Those two bricks kind of tied together, right? A big brick, a double brick, and object B, the single one, okay? So let's draw our free body diagrams. Just object A and B, we're about to let go of them. And so object A has a force of gravity acting on it, right? And object B has a force of gravity acting on it. And it's half as much because MB is half of MA, right? So we know the weight of A is twice as much as the weight of B. We're going to let go of these. And what's going to happen? One person might say, well, A is heavier. That means there's a bigger force of gravity acting on A than B. So it's going to have a bigger acceleration. It's going to hit the ground first. Right? Seems logical. Another person might say, no, wait. A is heavier. A is twice as much mass. A has twice as much inertia. It's going to resist changes in motion, and B is going to hit the ground first. A is going to, you release it from rest, it wants to stay at rest. It has twice as much inertia as the other one, and it resists that change in motion. B is going to hit the ground first. Okay, so both of those people are only looking at half of the equation, right? Our equation is, whoops, Newton's second law. Where did I put that? Right here. This is our equation, right? Newton's second law. One of those, pick one. I'll use the second one. The acceleration of those objects is the force, the net force, over the mass, right? So for the acceleration of object A is twice as much. It's 2 mg. I'm substituting in to get them both the same. Is twice as much force, and the mass is twice the mass of B, right? And the acceleration of object B is mb g over mb. So B has half the force, but it has half the inertia. So they both end up with the same acceleration. They both fall at the same rate, as long as there are no other forces acting on it, like air resistance. Okay? There's we all know that because there's air resistance. And the air resistance has a bigger effect on the lighter object. So one thing we could do, let's see, we could do this. We could change the object's shape so that air doesn't influence it quite as much, right? But let's not change its weight. So we'll change its shape so that the air doesn't have as much effect on it. We've changed its cross-sectional area, but we didn't change its weight at all. Now we're going to drop these. Which one's going to hit the ground first? Let's see. Ready? What do you think? Same time, right? So these are very different mass, these two objects, but they both hit the ground at the same time. The other thing you could do is this. Okay. I drop them, and we know the book hits the ground first. If I put the book on top of the paper and drop them, how do they hit the ground? Same time, right? If I put the paper on top of the book, how do they hit the ground?
The paper's going to catch some lift from the air.
What do you think? Should we look and see? You ready? Same time. The book pushes the air out of the way, and if there's no air resistance, the paper falls at the exact same rate as the book. It's only the air resistance that's causing it to fall at a different rate. Okay? You can amuse your roommates with that later.